Welcome back to General Chemistry Chapter 8, Gas Phase. In gas phase, we should know the general PV equals nRT equation. And before that, we need to know the three main ways MCAT uses the gas, using ATM as pressure, as standard, or in mercury, 760, or equals to torr as well, or 101 kilopascal. So kilopascal, remember that's times 1,000, so that's actually 101,000 pascal. Be sure to remember which unit to use. We also have standard temperature pressure, which is 273 Kelvin, and 1 atm, and this is usually to measure gases, right? And this is different from when we're dealing with standard state of 298 K and 1 atm, which is 25 degrees room temperature, with a lot of equations, especially with enzymes. And that typically deals with entropy, enthalpy, Gibbs free energy, changing energy states, uses standard states. Okay, the PV equals nRT, the generic combined gas equation, uses Avogadro's law, Boyle's law, Charles' law, Gay-Lussac to altogether create this equation. Now, because PV equals nRT, we could mess around with the equation because mass over volume is density, right? So we can substitute density into here and generate this equation. P, pressure, times the mass divided by RT gives us this equation, if we want to use that instead. We could also use PV over T over PV equals T for a generic way to quickly determine the change in a gas state in a container. Avogadro's law, think about constant pressure and constant temperature. We just want to know about the number of moles. And moles is N. N is the number of moles to deal with, and V is the volume. So if we have a new compound and it's a gas, right? And if it increases in a certain amount of molecules added, then the volume in respect should also increase to keep in constant. So if we increase N by power of 2, volume should also increase by power of 2. Boyle's law, think about boiling water, temperature is constant at really high, so PV equals PV. If we increase the pressure, the volume should, in retrospect, decrease at the same proportion. Charles' law, V over T equals V over T. If you increase the volume, then the temperature is going to increase at a set pace, in a set ratio also, right? PV equals nRT, so increase the volume should increase temperature by the same factor. Gay-Lussac is P over T equals P over T. So just like Charles, if we use P, pressure go up by a certain factor, Gay-Lussac says temperature should also go up by a certain factor. Dalton's law, just think about partial pressure. If you have NaCl, one compound NaCl, but that's not a gas. Let's use a gas. Let's say CO2. If we have an equation with one CO2, and that broken up into carbon plus O2, and O2 might consistently stick to one compound, but if we increase the number of compounds that it dissociates into, then that's going to increase the partial pressure, right? Because there's literally more of the molecules floating around. Think about if you have groups of 4 kids in a classroom, and you say, okay, kids, break up into your own seats, then that's going to take up more room, right? So Henry's law basically says solubility is in respect to pressure. So if we increase in solubility, pressure should also increase. So that should stay in the same proportion. Increase solubility, you should increase pressure by the same amount. Okay, and we also have average molecular speed determined by kinetic energy equals half mv squared. We know that from kinetics and force, but we can also use Boltzmann's constant, which is 1.4 times 10 to the negative 23, roughly, and times 3 over 2 temperature. That is just substituted for using the average mass of average speed of gases, Boltzmann's constant, is experimentally determined. We also have the root mean square. The root mean square of a certain. Okay, so we have two. So root mean square 3 times the gas constant times the temperature divided by m. So at certain temperatures, the gas is going to go faster, and m is in kg per mole instead of g per mole. So it's a big M. What this does is find out the traveling speed of the compound or a molecule, and we can compare two different molecules, R1 and R2, based on their mass. So if we have a hydrogen molecule and an oxygen molecule is 16 times bigger, so it's going to travel not 16 times but actually 4 times bigger, right? 16 over 1, that's 16. Root of that is 4, so it's going to travel rate 4 times faster than the other. Okay, so hydrogen is going to travel 4 times faster than oxygen because it's much smaller. And this is PV equals nRT, but the real gas equation. This is due to the attractive forces between the compounds, and this is due to the volume that takes up by the compounds. If the temperature is low enough, then that means the molecules are going to stick close together and they're going to actually attract each other, intermolecular attractions. And the volume is too small also, then that's also going to allow them to stick to each other. So by having low pressure, you're going to have high volume, right? So low pressure, high temperature is the ideal, get closer to the ideal gas law. All right, so that's basically about the gas.